In my previous video, I described to you the basic layout of the Milky Way Galaxy. The Milky Way Galaxy is an example of a barred spiral galaxy. The location of the solar system is about 2/3 or so away from the galactic center. The galactic center is about 30,000 light years away. And then it takes about 250 million years for the entire solar system to orbit the center of the galaxy. Ultimately, we can use those numbers, as I did in that example, to come up with an estimate of the number of stars that make up the Milky Way, several hundred billion stars, which is typical of a spiral galaxy, similar, for example, to our own. However, that calculation does not take into account, for example, a single object that resides at the center of the galaxy, and that's the Milky Way's supermassive black hole. What you're to do at this point is pause this video and then immediately go to the screencast that I've posted for you, which goes through the details of how we know that the Milky Way's black hole is in fact there. And it also gives you a basic idea as to how you could actually then use the orbits of some of the stars that are near the galactic center about the black hole to measure the black hole's mass. So go ahead and pause this lecture now and go ahead and watch that screencast. I've presented it to you as an Edpuzzle. Okay, now that you've seen that screencast, what we can then do is use some of the orbital parameters associated with one of the stars in orbit around the black hole to come up with an estimate of the black hole's mass. So I've presented it for us here as a problem. Okay, in that problem, I give you some of the details of that star. They are as follows. So the star in particular that we'll focus in on, and this was mentioned in the screencast, is the star that is designated as SO2. SO2 orbits the black hole with a period of 15.8 years in an elliptical orbit that has an eccentricity of 0.87. The star's closest approach to the black hole is 123 AU, 123 astronomical units. What we're going to do is calculate the black hole's mass in terms of what are called solar masses. Usually when talking about astronomical objects, such as stars, for example, and in this case a black hole, typically we don't talk about their masses in terms of kilograms because ultimately the numbers will be really large. Instead, we use a unit called a solar mass. In other words, how many times more massive than the sun is this particular object? Okay, let me go ahead and draw the elliptical orbit of this star about the black hole in the following way. Like so. So I'm drawing here a pretty eccentric ellipse. Okay, right here is the major axis of the ellipse, and right here is the center, like so. But ultimately the black hole resides at one focus as this star orbits the black hole. Okay, so right here is the black hole at the focus, and it has some mass. We're going to call this M hole, just to give it a name. Okay, and then we're given some numbers. Okay, first of all, the star's closest approach here to the black hole, like so, its perihelion position, if you will. This is what's given to us as 123 AU. And then we're also given the period of the orbit here. The period is 15.8 years. All of these numbers that I'm quoting here in this example, by the way, these are all measured as I described in the screencast. The eccentricity of the orbit E is given to us as 0.87. Now, just to give you an idea as to exactly how much gravity is present here, okay, this distance here, the closest approach of this star to the black hole, 123 AU, well, that's about 3 times or so the distance that Pluto is from the sun. In the case of Pluto, it takes Pluto over 200 years to complete a single orbit around the sun. However, in this case, this star takes only about 16 years to go all the way around the black hole, and its closest approach to the black hole is nearly 3 times the distance that Pluto is from the sun. This gives you an indication as to exactly how much gravity is present here that's causing all of this. This ultimately means that the mass of the black hole has to absolutely be huge. Okay, now, like the other examples that I've done thus far for gravitation, essentially all that this problem is an expression of Kepler's third law. So let me just go ahead and write Kepler's third law for this situation in the following way. T squared is equal to the following. 4 pi squared over g times the mass of the black hole, and then multiply by r cubed. Okay, the r here in this expression is the semi-major axis of the orbit. It's the semi-major axis of the ellipse. It's this distance right here. So what we're going to have to do first of all is find that distance. I'll do so in terms of astronomical units, and then we'll do some conversions and so on, and ultimately then solve for the mass of the black hole. When we do, we'll end up with a mass in terms of kilograms, and then ultimately we'll divide out by the mass of the sun to write the mass in terms of solar masses. Okay, now this distance here that the focus is to the center, if you recall, is some fraction of r. This distance here is ER, where once again E is the eccentricity of the ellipse. Okay, notice on the diagram that r minus ER is equal to what's given here is this distance of 123 AU. So r minus ER equals 123. And now let's go ahead and solve for r. So I'm going to go ahead and factor out the r here from these two terms like so. Take a look at this carefully. And then I'll divide by the parentheses now to get r, and when I do, I'll end up with an answer in terms of astronomical units. Okay, so r is equal to 123, and then divided by 1 minus e. So let's go ahead and get that number. Okay, so 123, and then divided by 1 minus 0.87. So doing the math here, ultimately then the semi-major axis of the ellipse is about 946 or so, 0.2 AU. Okay, now that I have that distance, now we've got to do the conversions. Let me do this here on the lower board. And I have to erase, by the way, the information that I still had here from the previous lecture. This was the galaxy problem. I still have it here on the board. Okay, so let's get rid of all of that. Okay, now let's go ahead and do our conversions. So first of all, r. Okay, r is 946.2 AU. I need to convert this into meters. Okay, the conversion factor is as follows. 1.5 times 10 to the 11th meters per AU. So let's cancel AU like so, and then we'll get this distance in terms of meters. So times 1.5 times 10 to the 11th. This is about 1.42 or so times 10 to the 14th. And this would be in terms of meters. And then we also have the period here of 15.8 years for this star as it orbits the black hole. I need to convert this into seconds. So 3.15 times 10 to the 7th seconds per year. Okay, years cancels. Okay, and that amount of time then is as follows. Let's see, multiplying all of this out. Let's see, about 4.98 or so, and then let's see, my calculator's in standard form. 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th seconds, like so. Okay, now I've got everything in the correct units. Let's go ahead and jump back up to Kepler's third law on the top board. And now what we need to do is cross multiply here and solve for the mass of the black hole. Okay, so the mass of the black hole is equal to 4 pi squared over gt squared, and then multiply by r cubed. So let's go ahead and multiply all of this out. When we do, we get an answer in terms of kilograms. Now the t is still here in my calculator, so let me go ahead and square that. Multiply it by the universal gravitational constant. I haven't written the value on the board, but recall from previous lectures that we know what it's equal to. Okay, let me go ahead and take a reciprocal, times 4 times pi squared, and then multiply by r cubed. So times 1.42 times 10 to the 14th raised to the third power. Okay, and then ultimately after all of that, you end up with an answer here is about 6.8 or so times 10 to the 36 kilograms. Okay, now to give you an idea as to how big this is, it's smaller than the galaxy's mass, of course, but it's still a large object. In order to give you an idea as to how large this object is, we'll now compare it to the mass of the sun. We will then calculate what is referred to as a solar mass, or solar masses, that is. All right, so let me erase. Okay, so for the Milky Way's supermassive black hole, the number of solar masses, here's how we'll write it, is equal to 6.8 times 10 to the 36 kilograms. And then what we do is divide by the mass of the sun, which is a solar mass, 2 times 10 to the 30th kilograms per solar mass. And then kilograms cancels out, and we'll end up with a number of solar masses. So divide out by the mass of the sun, 2 times 10 to the 30th, and this comes out to be about 3.4 or so times 10 to the 6 solar masses. A 10 to the 6th is a million. So this is about 3.5 million solar masses. that's the mass of the supermassive black hole at the center of the Milky Way Galaxy. It turns out that there are supermassive black holes at the center of all major galaxies, whether they be spiral galaxies, for example, like the Milky Way, or other types of galaxies such as giant elliptical galaxies. Ultimately, at the center of all galaxies are supermassive black holes. We don't know exactly where these supermassive black holes originally came from. The next generation of space telescopes that are being built right now are designed in part to answer that question. Nor do we know exactly the relationship between the growth of a galaxy and the growth of its central supermassive black hole. Once again, the next generation of space telescopes that are being built right now are in part designed to answer questions such as that. So galaxy evolution over long periods of time, we believe, are tied very closely together with the evolution of the central supermassive black holes that exist at the center of all major galaxies. It turns out that as impressive as the supermassive black hole is at the center of the Milky Way Galaxy, it's actually a relative pipsqueak compared to some of the other central supermassive black holes associated with some galaxies. In the next video, I'll introduce you to such an example.